So again, guys, the answers to the implicit differentiation review packet that you turned in this morning are on Fusion. They're in the notes and folders. You can see them. Their answers are in red. So that's the final simplified answer. So you may have to manipulate some of your answers to get down to that. I really like questions like 11 and 12 because it's not just about being able to find the derivative in calculus, it's about being able to apply the derivative. So we are, looking at being able to plug in those numbers and get down to a solution. Okay, so I figured I'd leave that up there since you guys maybe didn't have that and give you that opportunity to check them as we were discussing them. And again, I said don't worry about 15, 16 because they had trig. Okay. And we're good on the homework textbook then as well. We're good on the homework problems in the book. So looking at number 13, we have find our second derivative. So in order to find d2y dx squared, you have to start with the first. So the derivative of x is 1. The derivative of negative 2y squared is negative 4. Because 2 times 2, y, dy dx. And then derivative of 1 is 0. We are going to get the dy dx by itself, so we're going to divide by negative 4, y. So we get dy dx equals, just for space saving, negative 1 over 4y. Now when I do the second derivative, you can do the quotient rule. So d2y dx squared equals ho d high minus high d ho all over ho ho. So the first term zeroes out. A negative times a negative is a positive. But then again, we cannot have a dy dx in my answer. So we have to substitute it in with my dy dx from before. So you get 4 times negative 1 over 4y all over 16, because 4 squared, y squared. 4 times negative a fourth becomes negative 1 over y over 16y squared. So we get rid of our fraction and a fraction by multiplying by the denominator's reciprocal. So the denominator groups with the numerator's denominator, and you get negative 1 over 16y cubed. Okay? So we're going to pick up then with implicit differentiation involving trig functions today. So the rules still apply from before. You're going to look for any time you have two variables multiplied together, knowing you need to use your product rule. So we have to use the product rule in this case, not once, but twice. So we have first times derivative of the second plus the second times derivative of the first plus the first times derivative of the second. So derivative cosine is negative sine x. Derivative of the x is 1, so we don't have to worry about it. If cosine was to something other than x, then we'd have to take the derivative of that via the chain rule. So first times derivative of the second plus second times derivative of first equals derivative of 10, which is 0. Cleaning all of this up, you have x cubed dy dx plus 3x squared y minus y sine x plus cosine x dy dx equals 0. So we're going to leave the dy dx's on the left. And we're going to move the other material to the right. So you're left with x cubed cosine x dy dx equals y sine x minus 3x squared y. And again, I rearranged the terms just because I don't like to have a negative in front. And I simplified by leaving my dy dx values grouped together as opposed to adding a step where I DCF out later. So we have the x cubed plus cosine x dy dx equals y sine x minus 3x squared y. And then we want to get dy dx alone. So we're going to divide by x cubed plus cosine x. And we get dy dx equals y sine x minus 3x squared y all over x cubed plus cosine x. Okay? And again, guys, since we're on Zoom, if I'm ever doing something and you miss it or you want to save it, there's a little pen icon in the corners of some of your screens. If you click the pen icon, you can actually see you're able to write on the boards, but there's a save button at the end of that row. And that would allow you to save this screen as a picture in case you ever need what we're doing saved because you missed something or you're unclear and you want to go back and check on it. Or I guess if you're on a phone, you could screenshot. But just throwing out there, if you ever need to save a screen on a Zoom, you can. Okay, so then we're going to look at finding a derivative where this time we need the chain rule because the sign is being evaluated at x plus y. So now we have the inside isn't just simply 1. We need the chain rule. So finding our derivative, we start with the outside. The derivative of sine is cosine x plus y. But then the chain rule tells me that I need to take the derivative of the inside of cosine, which means I need the derivative of x plus y. So the derivative of x is 1. And then you have that dx, which we know becomes 1, plus the derivative of y, which is also 1, dy dx. So derivative of the outside, cosine x plus y. Derivative of the inside, 1 plus dy dx, equals the first, y squared, times derivative of the second, plus the second, times derivative of the first. Now this cosine x plus y is going to actually distribute to both parts of this. So you end up with cosine x plus y times 1, which is cosine x plus y, plus cosine x plus y times dy dx equals y squared secant squared x plus 2y tan x dy dx. So we're going to get the dy dx's on the left and the other stuff on the right. So you have cosine x plus y minus 2y tan x all times dy dx equals y squared secant squared x minus cosine x plus y. And then we're going to divide by the cosine x plus y minus 2y tan x. Leaving me with dy dx equals y squared secant squared x minus cosine x plus y all over cosine x plus y minus 2y tan x. Now, these cosine x plus y's cannot cancel. They cannot cancel. Because we have subtraction and or addition occurring in my numerators and denominators, you can't cross simplify like that. You can only simplify at this point if you could take out a GCF, and I don't have a GCF of every term. Therefore, I cannot simplify. My answer is done. So I'm going to leave that there for a minute because I know sometimes there's a little delay from what I'm writing to what you're seeing. in example number 3, we have two functions being multiplied together. So our first function is the 5 sine x, and it's being multiplied to cosine y. So I have a product rule occurring in this problem. So we have to take the first times the derivative of the second. So the derivative of cosine is negative sine y. But now, because the variable in there is a y, the derivative of y is 1 dy dx. So when we take derivatives with x's, it's dx dx's, which are 1s, so we're not too worried. But when we take derivatives with y's, we need that dy dx. So first times derivative second plus the second times derivative first. So you get 5. Derivative sine is cosine x. Derivative x is 1. Equals derivative of x, which is 1. And again, we have that imaginary dx dx, which we know changes to a 1. So cleaning this up, you get 5 times negative 1, which is negative 5, sine x, sine y, dy dx, equals 1. And I'm going to move over the cosines, so it's minus 5 cosine x, cosine y. So that left the dy dx's on the left. It brought over the non-dy dx's to the right. And then we have to divide and again, everybody wants to simplify those 5s. You cannot. If you really wanted to simplify, you would have to have turned this into 2 fractions, where you had 1 over the negative 5 sine x sine y, and then you had the 5 cosine x cosine y over the negative 5 sine x sine y, which would just give you a fraction plus a tangent x tangent y. So it doesn't do a whole lot of good. If the 1 wasn't in front of the cosine x cosine y, oops, I missed my x, then you could alter and change it. But as it is now, that's your answer. So, as you kind of saw a little preview, these get messy. They get tricky and they get complicated. So, it's all about taking your time, following your rules, and just making sure you don't lose product rules, making sure you don't drop dy dx's, and following the algebra. So we have our first times derivative second plus the second times derivative first equals the derivative of secant, which is secant tan. But that's not the tricky part. The tricky part comes from here, because you have to take the derivative of the x times y. So you need a product rule times the derivative of the secant. So it's secant xy tan xy times the derivative of the inside. So it's the first times derivative of the second plus the second times derivative of the first. So what that means is that in order to simplify and clean this up, I have to actually distribute the secant and the tan to inside those brackets. So go ahead, take a minute, and clean this up. Distribute, rearrange your terms, try to keep the x's first. So go ahead, give that a shot on your own. Okay, so hopefully upon simplifying that, you had 2xy dy dx plus y squared equals secant xy tan xy, bringing the x in front and dy dx at the end, plus y secant xy tan xy. Moving over dy dx's, you had 2xy minus x secant xy tan xy dy dx. And then if you had your other parts, you had y secant xy tan xy minus y squared. So hopefully everybody was able to get to that kind of on their own, because that's where we're headed, is can you find our derivatives and then simplify them? So I say it, I've said it once, I've said it twice, I've probably said it 1,000 times. Calculus itself is not hard. The algebra we have to apply within the calculus is the tricky part. Not losing signs, keeping our negatives, following our variables, and just really understanding conceptually kind of like the idea behind the simplifying. So you're going to divide both sides. And then we have this cluster of terms. I want you to notice every time I wrote the secant and the tangent, I bracketed or parentheses the x and y's. That's because you never want to not think that that is the angle. So oftentimes the mistakes I see in this unit have nothing to do with not understanding the calculus. It's the tiny errors, dropping those parentheses, losing a negative, missing a term that actually cost us our points. So I have GCFs in the top and the bottom. I could take out a y in the top and I could take out an x in the bottom. The thing is, bringing out that x and y doesn't help us. So there are times it's appropriate to look for GCFs. So I'm looking at the problem and I'm looking at that. But I'm looking and saying, well, does it help me? And if it doesn't help you, it's unnecessary. So, lo and behold, that takes us to our homework assignment in the textbook. And not sure if that totally matched what I had up on Fusion. So, yeah. 5 to 8, 23 to 30, and 41 to 42. So, you're going to work on that. I will be here on the Zoom call. So